8.3, solving right triangles. So far, we've known how to solve right triangles using triangle sum theorem to find some angles if we had two, to find if we were given two sides of a right triangle, we could find the third side using Pythagorean's theorem. Given two angles of a triangle, we could find the third one using triangle sum theorem. We also looked in lesson 8.2 that when we had an angle and a side, we could find other sides using SOHCAHTOA. Today we're going to be able to find all parts of the triangle, including angles, when we're given just sides. So be able to solve trigonometric ratios and find angle measures, be able to solve the right triangle for all parts, and be able to solve a right triangle on the coordinate plane. We'll probably do that in a separate clip, but it will be within the same lesson for 8.3. Example 1, identifying angles from trig ratios. Use the trigonometric ratio cosine of A equals 24 over 45 to determine which angle angle A is in this picture. So we're trying to determine whether the angle is angle 1 or angle 2 for that they used. Which angle did they use as they wrote the cosine of angle A? Well, remember, using the expression SOHCAHTOA, cosine is adjacent over hypotenuse. Well, if I used angle 1, then my adjacent was 1.4, this is for angle 1, and the hypotenuse is 5. Whereas if I used angle 2, the adjacent leg is 4.8, and the hypotenuse is 5. Well, most of us probably already know which one of these is closest to 24/5, but we could, if we want to, look at how we can convert this to be equal to 24/5. I would have to multiply the denominator by 5 and the numerator by 5, so 4.8 times 5. 4.8 times 5. I could also cross multiply and make sure that they are the same. 4.8 times 5 and 5 times 24. That's not right. This is 25. 4.8 times 25, sorry, and 5 times 24 both give me 120 if I do this cross product. So in fact, angle 2 is the angle that gives us the correct ratio. 4.8 over 5 is 24/25. Next, we're asked to do the figure out which angle is angle A when the trig ratio of sine is 8/17. Remembering SOHCAHTOA, sine is opposite, so our 8/17 is coming from the opposite over the hypotenuse. Well, 8/17 is angle A. If I'm starting at angle 1, the opposite is 27, and the hypotenuse is 30.6 meters. If I'm starting at angle 2, the opposite is, so this is for angle 2, 14.4, the hypotenuse is still 30.6. So I'll look and see which of these reduce to 8/11. I could also cross multiply to see if I get the same numbers. 8 times 30.6 versus 17 times 27. Yeah, those cross products are not equal. 8 times 30.6 and 17 times 14.4. Both of those give me 244.8. So I know that angle 2 is the angle they started at when they found the sine of angle A. That means angle 2 is also angle A for this picture. If you need some additional examples for this, they can be found in section 8.3 of the geometry textbook. Inverse trig functions. There are actually more than just sine, cosine, and tangent. There are 3 trigonometric functions. A function is something that has a relation. So for now, if we look at a table, let me see if I can find an angle table real quick. So I couldn't pull any up on the web, but I have this from an exploration I used to do with regular geometry. For every angle, we already know that this does this for 30, 45, and 60. You guys wrote those out for the exact values of sine, cosine, and tangent. And it doesn't matter what size triangle, if the angle is 30 degrees, the ratios for sine is always going to be the same exact value, or for 25, the exact, or a decimal approximation of 0.4226. Well, we'll look at this in we've looked at this in our calculator as well. So here's the thing. What we have is a function. If I put in cosine, what was that angle? Cosine of 25, or sine of 25 degrees. That is my input, is the 25 degrees, and it gives me the output 0.4226, which we see on that sheet. If I put in cosine of 25 degrees, it doesn't matter the angle, it can pick any angle from 0 to 90, actually beyond 2, but we'll look at that later. We can see that that is 0.90631 if we round out. So in doing that, we can actually, yikes, where'd it go? Right there. We can see that that works. That is a function. You input the value. So right now we have trig functions. Trig function of the angle gives us the ratio as a decimal approximation. The trig ratio of an angle. You put in sine, cosine, or tangent, one of those trig functions, plug the angle in, it gives you a ratio. But there's actually 3 more trig functions or trig ratios. And so the ones that we're familiar with are sine, which is opposite over hypotenuse, sine of an angle. Cosine of an angle, I'll use theta, is adjacent over hypotenuse. And tangent of an angle is opposite over adjacent. And we can memorize that using SOHCAHTOA. But there are what are called cofunctions. Along with sine, its cofunction, or reciprocal or inverse, sometimes this is called reciprocal trig function, is cosecant. It's written cosecant, but it's abbreviated CSC. Cosecant is the reciprocal of sine. It is the hypotenuse over the opposite. We also have secant, which is the cofunction with cosine. Secant is defined as the reciprocal of cosine, hypotenuse over adjacent. And then lastly, we have cotangent. It's not said cot, just like sine isn't said sin or cos. This is sine, cosine, tangent. This is cosecant, secant, and this is cotangent. Cotangent of an angle is the adjacent, the ratio of the adjacent over the opposite. Now you don't see these keys on your calculator per se. You can attain them on some calculators, not all. But you could also just get the ratio and do the reciprocal value, and you've got these inverse trig functions. Now, here's something else. Oh, shoot, I think I did not do what I was supposed to. Hold on. No, that's right, because we're going to use that. Inverse trig functions. Nope, that I've defined this already. So let's go back to my discussion here. Trig function of the angle is equal to the ratio. So if I say plug in sine, put 25 into the sine function, it gives you this ratio. Well, we're talking about inverses. Inverses like, and you don't have to write this part down, but inverses like the multiplicative inverse of 3. How do I do that? I multiply it by its inverse, which is 1/3, or divide by 3, and I get x by itself. The additive inverse of 2. Well, I add the additive inverse, which is -2, and those go away. I end up with x equals 6. Same idea here. I have sine of 25 degrees equals 0.4262. To undo sine, I would use its inverse, and I would get 25 degrees is equal to, oh, you can't see that on your screen. See, I have sine of 25 degrees equals 0.42262. If I do the inverse of sine, it will undo sine, and it will give me, so this isn't the reciprocal value, this is the actual inverse function, just like squaring and square root, right? I had 9 squared, I take the square root, I get 9 back. Same idea, the inverse undoes the original function. 25 degrees equals sine inverse of 0.42262. Now it's not going to be completely accurate because they have a rounding thing there, but let me take a look. Sine inverse of 0.42262 pretty much is 25 degrees. If I do sine of 25 degrees, I get that decimal value. If I do sine inverse of it, I get the angle back. That's what inverse functions do. So here's where this is going, and I'm sorry I went through all of that again. That's not this section. We already know that from our previous notes. That if you're trying to solve for the measure of the angle, you need to use the inverse trig ratio, not reciprocal. Inverse trig ratio. The measure of the angle equals the inverse trig of the ratio. So that's what we did in our calculator. We said, hey, we know the ratio is 0.42261 or 62. We did sine inverse of it. It gives us the angle back. So we use regular SOHCAHTOA when we're solving for sides, and when we're solving for angles, if we know the trig ratio, we can use inverse trig functions to get the angle measure, solving for the angle measure. So here's the idea. They know the trig ratio. This is the trig ratio for cosine of whatever angle A is. I don't know what angle A is, but I know the trig ratio. I don't know what the side lengths were, but I know they reduced to 0.87. If I want to solve for angle A, the measure of angle A is going to equal cosine inverse of that ratio. So in my calculator, I do cosine inverse of 0.87, and I get 29.5. They asked me to go to the nearest degree, so that is roughly 30 degrees when I round to the nearest degree. For letter B, the sine of angle B. So in some picture like this, I had an angle B, and they did the ratio of opposite over hypotenuse, and they got the ratio to be 0.85. But they want to know what the measure of angle B is. So I'm going to do sine inverse of that sine ratio. Sine inverse of 0.85 gives me 58.2 rounded to the nearest degree is 58 degrees. And lastly, tangent of C. If I want to know the measure of angle C and I know its ratio of tangent, then I just have to do the inverse trig function of the ratio and it will give me the angle. Tangent inverse of 0.71 gives me 35.4, so 35 degrees. 35 degrees. Solving right triangles. We have several things that we can use. We can use, if you're given two sides, you can use Pythagorean's theorem to find the third side, and regular SOHCAHTOA and inverse trig to find the angles. You'll see this in an example in a second. So if you're given two sides, use Pythagorean's theorem to find the third side, use inverse trigonometry to find the angles. And we would, for all of those, we'd want to use the sides that were given for two reasons. One, if I calculated the third side wrong using Pythagorean's theorem and I made a mistake somehow, then all my answers calculated based on that number will also be wrong. And secondly, because just for accuracy purpose and rounding, we want to make sure we use the original sides when possible to calculate all the other parts. The other type of problem you'll have is where you're given one angle and one side. Given one angle and one side, I can use regular SOHCAHTOA. I might have to use it more than once to find the sides, to get the other sides. And because we're doing right triangle trigonometry, if you know one of the acute angles, then you can use the triangle sum theorem to find the other angle. Let's take a look at how this is done in the next example. In this problem, they have given me no angles. So I know that because I have two sides and I have no angles other than the right angle, because we're doing right triangle trigonometry, that to find the angles, we're going to have to use inverse trig. To find the sides, I have two of the sides. To find the sides, I'm just going to use Pythagorean's theorem. Well, that part's easy. So to find ST, ST squared plus 5 squared equals 5.7 squared. You're very familiar with this, so I'm going to do 5.7 squared. I'm going to take away the 25. This gives me ST squared equals 7.49. I'm not going to worry about exact value because it says round lengths to the nearest hundredth. So I'm going to do the square root of that, and I get that ST is roughly my calculator says 2.736. So rounding to the nearest hundredth, 6 is bigger than 5. 5 or higher, I round up, so it's 2.74 for ST. Well, we found the other side. Great, I know that that's 2.74. I should not use that side when I'm calculating angle values. I should only use the lengths that were given. With respect to angle R, the 5 is the adjacent, and the 5.7 is the hypotenuse the whole time. So we go back to SOHCAHTOA. I have the adjacent and the hypotenuse, so I'm using cosine for angle R. So I'm going to say the cosine of angle R is adjacent over hypotenuse. Well, I know the ratio. I don't need to know the decimal value. It's fine, just like that. I have a ratio. This means that the measure of angle R will equal cosine inverse of 5 over 5.7. Cosine inverse. Before, you guys were just setting up the ratios. If I said, what's the cosine of angle R, you'd say, oh, that's 5 over 5.7. Well, using inverse trig functions, we can actually figure out, or the calculator will tell us what the measure of that angle is. So cosine inverse of 5 over 5.7 is 28.69, so 28.7, except they said for angles to round to the nearest degree, so it'll actually be 28.629 degrees. So there's the measure of angle R, 29 degrees. When I go to find the measure of angle T, the 5 is no longer the adjacent. The 5 is now the opposite. The 5.7 is still the hypotenuse. So I have a different function. I have sine. Sine of angle T is 5 over 5.7. This means that the measure of angle T is equal to the sine inverse of 5 over 5.7. I know the ratio. The calculator has a mapping between the ratios and the angles. So if I put this in, it'll tell me what the angle is. Sine inverse of 5 over 5.7 gives us 61.3, so 61 degrees. The last thing I want to do is make sure that these two add up to 90, so that my triangle's angles don't add to more than 180. And in fact, that's 89 plus 190 degrees. 90 and 90 is 180, so we are good. They gave us the right angle and two sides. We now know the other two angles and the third side. We have solved this triangle completely. For letter B, we're going to undergo the same process, except this time they gave us an angle, so it's very easy to find the other angle using the triangle sum theorem. 180 minus 90 is 90, and 90 minus 58 is 32 degrees. That was easy, and we have the 32. But when I find my other sides, I don't know this side and I don't know the hypotenuse. I can't use the 30, 60, 90 or 45, 45, 90 triangle because that's a 58 degree angle. But I can use SOHCAHTOA to find the other sides for this problem. So for this problem, the 14 is the opposite, and I'm going to find x first, which is the adjacent. Opposite and adjacent is the tangent function. So the tangent of 58 degrees equals the opposite over the adjacent, 14 over x. This should be familiar to what you did in the 8.2 lesson. We cross multiply, we get x times tangent of 58. degrees equals 14. We divide by tangent of 58, so 14 divided by tangent of 58 degrees. I'm not solving for the angle, so I'm not using tangent inverse. I'm solving for the side, so I'm using regular tangent. So this gives me roughly, and they said to the nearest hundredth, so it was 8.748. This rounds to 8.75. And they didn't give us any units, so I don't have to worry about putting meters or inches or miles or anything like that. The other side that I'm solving for is y. So again, I'm going to use the 58. This is still the opposite of the 58 degrees. The y is the hypotenuse. So opposite and hypotenuse is so. So I have the sine of 58 degrees equals 14 over y. I'm going to cross multiply. I got y times sine of 58 degrees equals 14. And divide y equals 14 divided by the sine of 58 degrees. When I put that in my calculator, I get 16.508. Rounded to the nearest hundredth is 16.51 for the value of y. We now have all three angles, the right angle, the 58, the 32 that we solved for. The 14 side was given using SOHCAHTOA. We solved for side EF and for side FD, which I should probably call those EF and FD, but I gave them variables just to make it a little easier in the solving process. The next video will show how to find angles, or how to solve for triangles in the coordinate plane. This video showed you how to solve for all things in a right triangle, using SOHCAHTOA to help you find sides, or Pythagorean's theorem, depending on the setup of the problem, or using inverse trig, inverse of sine, inverse of cosine, or inverse of tangent to find angles, and or triangle sum theorem to find angles. So please watch clip 2 of 8.3 to see the back of these notes.